Hi, I'm Alex Tom, and today I'll be talking about our paper, Diffusion Earth-Movers Distance and Distribution Embeddings. Today, we are concerned with distances between probability distributions. One common example of this is the tilde variation distance. This distance has wide applications, but has a few drawbacks. Namely, for distributions of non-overlapping support, the tilde variation distance is always 1. And this is true even as things get arbitrarily close. Another distance between probability distributions is the Earth-Movers distance, also known as the Washington distance. Intuitively, this distance measures the amount of work it would take to move Earth piled at one distribution to piles defined by another distribution. This Earth-Movers distance does not suffer from the problem described previously, but suffers from computation challenges. In the primal form, this computation scales with O(n cubed for exact solutions and O(n squared using entropic regularization. Today, we will consider computation using the Cantor-Rubinstein dual form, which integrates a Lipschitz continuing function against the difference of the probability distributions and is equivalent to the primal form under some mild assumptions. There are many ways to optimize over this constrained witness function. However, today we will look at a particular form, namely when the witness function is expressed as a collection of wavelets. In this case, the witness function, and thereby the Earth-Movers distance, has a closed form in terms of the difference of coefficients of the two probability distributions in the wavelet domain. This was termed wavelet EMD in earlier work by Schrodhanger and Jacobs. However, the number of wavelets scales exponentially with dimension, posing a challenge for high-dimensional data. In this work, we propose a graph-based solution, which does not depend on the ambient dimension. Diffusion wavelets on graphs can be defined similarly to wavelets in the Euclidean domains, using a diffusion operator P. We illustrate how successive applications of P propagates point masses over a graph, with points sampled uniformly from the unit square. Using diffusion wavelets gives the full picture. For M high-dimensional datasets, we can first define a common data graph, then compute a vector of wavelet coefficients for each distribution of the graph, where the L1 difference between these vectors gives the diffusion Earth-Movers distance over the graph between their respective distributions. Embedding distributions of vectors in L1 is useful because we can exploit the vector geometry to form fast nearest neighbor search. This computation scales log linearly in terms of both the number of points and in terms of the number of distributions for EMD nearest neighbors, which contrasts with the typical quadratic or cubic scaling of other methods in terms of points and distributions. The diffusion Earth-Movers distance can be written as follows. Notice that we can compute all tk for a given distribution before taking the difference, which is computationally advantageous. Importantly, we show that the diffusion Earth-Movers distance is equivalent to a Washington distance with a manifold geodesic ground distance as the sample size grows large. In this paper, we show that the diffusion EMD, by using soft bins, recreates the manifold ground distance more accurately than comparable methods using discrete bins, which are often described as true Washington distances. Here, we show the EMD for 3 methods between a Dirac at 0.5 and other Diracs positioned along the line graph. We also show that the diffusion Earth-Movers distance is more accurate for a similar computational budget as compared to these tree methods, and orders of magnitude faster than even a fast synchronous implementation for nearest neighbors over 1,000 distributions. This is due to embedding these distributions into vectors and exploiting their geometry. Finally, we show that the diffusion Earth-Movers distance can be applied to a large single-cell transcriptomic dataset of over 20 million cells. We can use these to embed COVID patients based on their immune cell state. Here, we measure the states of tens or hundreds of thousands of cells from each patient, which creates a distribution over cellular states for each patient. We then compute patient similarities using the diffusion Earth-Movers distance between patients and show this creates a more useful embedding than similarly efficient methods. In summary, diffusion Earth-Movers distance embeds distributions on the graph to vectors, where the L1 norm between vectors is equivalent to the EMD between distributions over a common manifold. By using a geodesic ground distance, we skirt around the problem of high-dimensional data, scaling instead with the intrinsic dimensionality of the manifold. By operating over a sparse graph constructed from data, we avoid computing and optimizing over a pairwise distance graph. And finally, for EMD nearest neighbors, we can avoid calculating all pairwise Earth-Movers distances by embedding to a vector space and exploiting the L1 geometry between vectors. Thanks for listening, and for more details and our code, you can see the links above.